Hi there, welcome to lecture 21 of Machine Learning from Data. We're going to continue talking about neural networks and specifically fitting the data to obtain your final hypothesis G. And in order to do this, we're going to talk about forward propagation and backward propagation, two famous algorithms that are really what brought neural networks back into the limelight in the mid-80s and early 90s. Okay. But we will have to address the issue of are we fitting the data or are we overfitting the data? Okay. So lots to come. Now, quickly, what did we do last time? Last time we introduced the multi-layer perceptron that demonstrated the awesome power of being able to cascade linear perceptrons. And basically now we can implement any function to within any given accuracy. Okay, so we started with the biological inspiration of neurons in the brain, and in the bottom left we see the engineering device, the neural network at a high level in all its glory, which is what we're going to use. Okay, so this is just to show you that biology gave us the inspiration, but engineering success might require something that looks a little bit different. Okay. And last time we developed a notation for the neural network. Okay, and so if you drill down deep into what's going on at a particular node in your neural network, which is a feed-forward multi-layer neural network, okay, there are inputs to a node which we call SL, and outputs from a node which we call XL. The inputs to the node came after multiplying by weights connecting to the layer L, and the output for the node, is going to get multiplied by weights connecting to the layer L plus 1. Okay. And in this way, you can think of, you initialize the network on the left and with your features, and then those propagate to inputs of the next layer, and then outputs of the next layer, and then inputs of the next layer, and so on. And so the input features propagate all the way to the output final layer and produce your final hypothesis h of x as shown in this picture. Okay, and we summarized this notation. So into a layer are the signals SL. We can collect them into a vector, okay, a DL dimensional vector. The outputs are XL, okay, which is DL plus 1 dimensional vector. The plus 1 is because it's augmented by the 1. Okay, and then the weights into layer L we denoted by the matrix WL. Okay, and the weights out of a layer we denoted by the matrix WL plus 1. Okay, now don't worry, we'll go over these notations again on the board. Specifically, we'll first have to decide, how do we compute the output h of x for the neural network? And in particular, what does it depend on? Well, it clearly depends on, the inputs, which you initialize the network on at the left, so x1, x2 up to x sub d. But then it depends on all the weight matrices. Okay, so all the weights on the edges, and I'm allowed to tune those weights. That's what gives me the awesome power in the neural network. So we will sort of heuristically represent all these weights by the parameter capital W, okay, which has the weights into layer 1, the weights into layer 2, the weights into layer L, okay, the output layer capital L, okay, and all these L weight matrices comprise all the parameters that we get to tune in the neural network. So we can specify, and each of these weight matrices W1, W2 up to W big L are matrices. Okay, so W is a collection of L matrices, and if you specify these L matrices, you have actually specified the network, and implicitly you've also specified the architecture, and we'll see how that works. Okay, and now we get to choose these weight matrices in order to fully specify the hypothesis h of x, and then the question becomes, how do we choose them? We need to fit the data. Okay, so we need to choose them to fit the data, and that's the topic of today. So let's go to the board. I've redrawn the neural network here, and let's go through it, to build some intuition for what's going on. So in the first layer, we have our input features, the augmented one, feature 1, feature 2, up to feature D. So this input layer has dimension D, okay, and it has D plus 1 nodes. Okay, now what's going on? So in the next layer, we have, in this example, 3 nodes, okay, and each of these nodes is essentially computing a perceptron on the previous layer. Now, it would be a perceptron if this theta was a sign, but we're going to soften the sign and make, everything more mathematically convenient by using tan h. It's an approximation to sign. Okay, so theta is going to be tan h. But effectively what's going on is this vertex, this node in layer 1 is computing the red perceptron of the input. This node is computing the green perceptron of the input, and this node is computing the blue perceptron of the input. Okay, so we compute 3 perceptrons on the input, and for each of these perceptrons, you have the red weights, the green weights, and the blue weights. And so we store each of these weights as a column in the weight matrix W1. 1 for layer 1. Okay? Now, each of these is computing a perceptron, so they have an output. So this layer has an output vector. Okay? And so what's going on in the next layer? Each of these nodes computes a perceptron, the red perceptron and the green perceptron, for the output vector that's produced by the previous layer. Okay, so you have 2 perceptrons being computed, and the weights for those 2 perceptrons are stored in the weight matrix W2. Okay? And then these perceptrons have output. Together with the augmented one, we compute a final perceptron in the final layer and output h of x. So what does h of x depend on? Well, certainly depends on what you put for the inputs here. Okay, what are the input features? But what else will change h of x is if you change any of the weights. So h of x depends on these weight matrices and and the input data. Okay, now let's drill deeper into a particular node. So I've highlighted a node in layer L, node I. Okay, so this node will have an input, and we will typically call that input SLI. Okay, so there'll be an input to node 1, to node 2, to node I, to node DL. DL is the dimension of layer L. So there'll be DL inputs. I can collect all those inputs in a vector. I call this vector SL. Okay, so what's the dimension of this vector SL? It's exactly DL. There's SL1, SL2, up to SLDL. Okay, so this input vector into the layer now, okay, which is composed of each of the individual inputs to each node in the layer, is a vector of dimension DL. Okay. Then we can compute the output, okay, from this layer. Okay. And each node in this layer, okay, produces an output. So for example, node Li produces the output XLI. Okay. And I can collect all these outputs in a vector XL. Okay, and I put the augmented one. So I have the output vector from this layer, XL, which is 1. Okay, then XL1, the output from node 1, from node 2, from node I, from node DL. Okay, so there's 1 plus DL outputs from the layer. So the output vector XL is 1 plus, has dimension 1 plus DL. Okay, so that's the output vector. Okay, and we're focusing on specific node and a specific layer L. Okay. So let's see, how do we compute the input to this node Li? Well, it's basically the signal. The signal we're basically computing as input signal, which gets transformed by tan H. This input signal is basically a perceptron, the linear signal. Okay. So how do I get this input signal? I have a red perceptron because it's a red. I've colored this node red. So I implement a red perceptron on the previous layer's output. Okay. Now, what's the dimension of the previous layer's output? Well, the previous layer had dimension DL minus 1. Okay, so if you augment it with the 1, then the output vector from this layer has dimension 1 plus DL minus 1. Okay, so that's the dimension of this output XL minus 1. We compute a perceptron, we compute a linear signal, okay, on this output, and this red perceptron, which is one of the columns of weights in WL. So we compute this red perceptron. That's the input to signal to this node Li. Okay. And then we output it and we deal with it in the next layer. Okay. So this perceptron, this red perceptron weights are stored in this weight matrix WL. This weight matrix WL is going to have a perceptron for each node in this layer, because each node is computing a perceptron. Okay. So how many perceptron weights does it need to have? DL. Okay. So if we drill in to this weight matrix WL, it has a set of perceptron weights W1 for layer L, W2 for layer L, it'll have WI for layer L, all the way to WDL for layer L. Okay. So there are DL perceptrons which are stored as columns in the weight matrix WL. So this weight matrix WL has width DL. DL columns. Okay, and what's the dimension of each of these perceptrons? Each of these perceptrons has a dimension which is corresponding to the augmented output from the previous layer. Okay, so the augmented output from the previous layer has dimension 1 plus dimension of layer L minus 1. Okay, so 1 plus DL minus 1. Okay, so this weight matrix is a DL is a 1 plus DL minus 1 by DL dimensional matrix. Okay, so now let's mathematically define how we propagate the feature vector forward in this network until we ultimately get the final output h of x, and this is called the forward propagation algorithm. Okay, so how do we compute h of x? And it's all really embedded in this discussion of what's going on at a node. Okay, so let's come back and we're going to discuss forward propagation.